All right, welcome back, guys. So this would be just a video on 2.2 and 2.3. In the previous video, we discussed how to organize data using the frequency table, and there's some terminology regarding frequency table. Not too crazy with the terminology. They're pretty straightforward. In this video here, we're gonna look at some of the standard graphs that we use to organize data as well. The two definitions I have written down here are the two we will go over, at least one of them. Keep in mind that anything with graph, when it comes to data, we're going to use technology, not quite graphing by hand. The first definition we have a blank displays the distinct values of qualitative data on a horizontal axis and the relative frequencies of those values on vertical axis. The vertical bar whose height equal to relative frequency, that the value represent the relative frequency of each distinct value. The bars should position so that they do not touch each other. So we have these two things that we want to highlight here. So this graph display values of qualitative data on the horizontal axis, and then the bars should be positioned so that they do not touch each other. So if we have a graph that satisfy this definition, we're going to call this a bar graph. So a bar graph is used for qualitative data, and then we also have a histogram. This will be used for quantitative data, and then the bars should be positioned so that they touch each other. So those are the main distinction between the two graphs. They looks very similar, but we want to pay attention to minor details. One is being used for qualitative, the other one is for quantitative. In the previous lesson, we look at a quantitative data frequency table, and we can graph this too. However, I rather just show you guys how to graph the qualitative graph, which is the bar graph on this example here. It's a much easier one to do. All you have to do is just create a frequency table and then just kind of label the horizontal axis based on the category. In this case, is the letter grades. So the first thing we do is we're gonna organize the data by using the frequency table, right? So for letter grade, we have A, B, C, D, F. So we have A, B, C, D, F, and we're just gonna count how many A's are there. So let's see here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 A's. And let's see here. B, you got 1, 2, 3, 4, 5, 6, 7 B's. And then C, we got 1, 2, 3, 4. So 4C. And then D, we have 1, 2, 3, 4, 5D. And then F, we got 1F. Okay. So this is a frequency table for a qualitative data set. Now we can actually draw the bar graph. So when we label this, we label the horizontal axis as letter grade. Okay, and then this would be frequency for the vertical axis, right? So we said, all right, so there we can do A, B, C, D, F, and then we can say A, there's 9, so let's say 1 to 9, so let's do 1, 2, 3, 4, 5, so this would be count by 2, so 8, 6, 4, 2, 0. So for A, we can say this will be B and C, D, F. Actually, the bars are not going to touch each other, so we want to give some space here. So A, there are 9 counts. So 9 is up to that there. So that's 9. Let's label that as well. And then B, there are 7. So let's say B7, so it's right there. All right, 7. And then C is 4. D is 5. F is 1. Okay, 1, 5, 4, 7, right? So this would be an example of a bar graph. Notice that the rectangles, the bars don't touch each other, and then this is being used to display qualitative data. Pretty straightforward. And the histogram is very similar too. It just the tricky part is label the horizontal axis and also make sure the bar that are touching each other. And in this example, he's asking what percentage of students are that pass the class. So we're gonna say this right here, right? So that would be what, 20 out of 26. So 20 out of 26. What percentage is that? 80 something. Let's see here. So around 77%. So that's how you sketch a bar graph. Okay. Another graph I want to go over is this is called a dot plot. So a dot plot is a graph that consists of quantitative data, okay, in which each data value is plotted as a point or a dot above the horizontal scale of values. Dots representing equal values are stacked. Okay. And I got a data set already for us. So this is the data set of volumes of soda by ounce. So we want to graph a dot plot. So let's see, if I want to graph the dot plot, I want to draw the horizontal axis. Okay, and then I'm going to label this. Okay, so let's say I have data value ranges from 50 to 85. So I can do by an increment of 5 or 10. Okay, so what I'm going to do here is I'm going to start with 50. So this is be 50, 60, 70, 80, and then in the middle will be, increment of 5. So 55 will be in the middle. So let's see. So this will be 55, 65, 75, and then 80, right? 85, sorry. Okay, so first we got 150, so that's one dot above 50. 75s, we got 1, 2, 3 75s. 65s, we have 1, 2, 265. 70, we have 1, 2, 3, 470. And 80, we have 1, 2, 2 80s. 85, we have 1, 2 85s, right? So that is the dot plot of this data set here. And we should be able to have 12 dots because there are 12 data values. Actually 14. 1, 2, 3, 4, 5, 10, 14. So 1, 2, 3, 4, 5, 6, 7, 10, 14 dots here. Yep. All right. So, and another graph I'm going to show you quickly is called, so this is called dot plot. And another one we're going to call this a stem leaf. So it's kind of like the dot plot, but it's being displayed vertically. So we draw a vertical line, and then the stem will be on the left. The stem will be on the left, and then the leaf will be on the right. So the stems are the tens, the 10 place value. So we have 50s, 60s, 70s, and 80s. So we have 50, 60, 70, and 80s. Those are the stems. And then the leaves will be the 1 digit. So we have, for 50s, we have 50, which is 1 0, and then that's it. And then for 60, we have 65, and that's about it, I think. Okay. And then for 70, we have 0, which is 70s, 3 70s, actually 4 70s, and then 2 75, 3 75s. 375. And for 80s, we have 2 80s, and then we have 2 85s. There it is. So this is an example of stem leaf. And you can see if I were to draw a density curve through this, we kind of see the distribution very similar, right? So you look at this way, and then it's kind of like very similar to that. All right, so two different ways represented data. One is dot plot, the other one is standard leaf. Sometimes data set, once we plot it and we graph it and then we draw the density curve through this, it have this special shape called the bell shape, and this is called the normal distribution shape. So this is normal, in other words, bell shape. And then just quickly about the distribution, not so much about it, but we're gonna learn a lot more about normal distribution in chapter 6. So a shape distribution has a bell shape. This is going to be a symmetric at the mean. Okay, so let's say if here's the mean, then to the left to the right that are symmetric about the mean there. It goes from increasing, decreasing, and then it behaves the same thing again. So it turns out another properties of normal distribution is that the mean equal to median equal to the mode. We don't know what this means until we hit chapter 3, but just this is just a quick brief introduction about data set that has a bell shape alike. Okay, there's other type of distribution as well. When you have a shape of a data that is kind of skewed, we have a data set that's skewed to the right, or positive skewed if the distribution has a longer right tail, and then if the data set is skewed to the left, we also know as negatively skewed, then the distribution has a longer left tail. So let me sketch what those type graph may look like. So you can have a data set that is like that. So you have a longer left tail, and then whereas another one like this here. Right, so a longer right tail. So this would be right skewed, and then left skewed. Right. Some example regarding left skew and right skew data. So if we look at right skewed, for example, so for right skew data, some example in real life that we can think of would be if you look at annual incomes. So let's say example would be annual incomes for US adults, right? So if this was money or incomes, then majority of us are in here, and then maybe a few of us are in this here, where that's where the 6 figures, the high end or the 1% high income. So that would be an example of a right skewed distribution. For left skewed distribution, let's say if we want to use example of this would be lifespan for human. So this would be year, right, in year. So let's say we start at 0 here, then many of us would die somewhere up here, majority of us, right? If there's only a few of us die young, right? So look, maybe this would be like 60, or so that would be a left skewed distribution example that we can think of there. Some graph can be misleading and want to depict a certain way, so the audience might misinterpret it. So I'm just gonna go over one example of how a graph can be deceptive. Here's a graph or a result of a graph that showed the result of adult survey, and the question was asked how comfortable they feel being inside a self-driving vehicle. Okay, so here is the graph. So we're looking at a lot of people say no compared to yes, and if you look at the picture, the 2 bars, one is almost 5 times proportionally to the other one, like the no, right? So that is one misleading there, because if you look at the vertical axis, it doesn't start at 0. So if this would start at 0, if we extend this down further, let's say 100 and 0 right there, 0, 100, right? If we start that down there further, if we start at 0, so it won't look as much as you know before. This right here won't be as large as compared to this one. Now we have an actual correct starting value, right? So the misleading in this case is because the graph, the vertical axis does not start at 0. The proportion of people said no seem to be 5 times as the people said yes, but in reality it's about 2.5 times more than yes, right? Would you agree? So some graph will do that. They'll zoom in a certain angle, and they want you to think a certain way, and that's trying to persuade you. Kind of like online dating. You know, if you take your best picture of yourself, a certain angle, when you take a selfie, and it come out good, and then you know, you may not look like that in real life. So I'm not saying I have personal experience with that, but that just give you an example that media can be very misleading. So yeah, so it's important to know, you know, how to tell when a graph is misleading, so that way we don't get a misinterpretation from the data set. I think that's all I want to cover for 2.2, 2.3. Pretty straightforward, 2 sections. The last one is kind of difficult because we are gonna use some technology to do this here. So I'm gonna do that on the next video on 2.4.